Okay, so good evening, everyone. Uh,
Good evening.
yeah. So, before starting today's session, I'd like to introduce myself. I'm Moina Ghoshal. I'm a PMRF at IIECR Kolkata, and I have been assigned as a TA for this course, which is entitled as Applications of Spectroscopic Method in Molecular Structure Determination, where this course will be helpful for you to elucidate the chemical structures from the given data. So in the previous five week assignments, we have seen that if any NMR data or any mass data is given, from there we can analyze any spectrum, and from that we can identify which kind of molecule it is, and also from the mass we can identify what kind of fragments are present in the molecule. That we have seen in the previous days, previous 5 weeks. Okay, so 3 weeks we have spent in NMR, which was basically very much needed, and because also from this NMR we have done two types of NMR, which one is proton NMR, one is NMR, and one other is 13C NMR. And then this week 4 and week 5 we have learned about mass spectrum. Okay, so where in mass spectrum we have seen that from the different kinds of mass techniques which are available, and from which we can identify what kind of fragmentation is happening in the system, what kind of fragments are produced, and from that we can also predict the structure of the compound. Now, from NMR and from mass, these two techniques will be helpful for you to identify which kind of molecule it is. Now, to give more idea about any kind of functional groups of any kind of bonds which is present in a molecule, there is another type of spectroscopy which is generally used by the people, which to use to confirm that whatever groups or whatever functional groups that you are talking about is present in your molecule of interest, is this present in your molecule, in the molecule that you have solved. Okay, so to confirm that, people usually do another kind of spectroscopy, which I am going to talk about today, which is also known as infrared spectroscopy or vibrational spectroscopy. Why vibrational spectroscopy? Because molecular vibrational levels are generally probed using this spectroscopy. So generally, this 400,000 to 400 centimeter inverse region in the electromagnetic spectrum is actually important, because most vibrational transitions occur, organic functional groups occurs here. So if this is an electromagnetic spectrum, you see this region of 4,000 to 400 centimeter inverse. So their unit is given on a different way, but this region, this infrared region, this region is actually important to elucidate this molecular structure, because in this region generally organic functional groups which are present in the molecule, they actually vibrate in this region. So if you illuminate any kind of organic moiety with some electromagnetic radiation of infrared frequency, you will see that different functional groups actually absorb this infrared radiation differently. So if you have learned about, I don't know whether you know about this absorption or Lambert-Beer law. I think I have talked about in the very first lecture, that if you know that how to get this transmittance, that molecule light is passing through a molecule is absorbing something and it is transmitting something. Okay, so from this transmittance spectrum, when if you are plotted against this range of energy, you will see that which kind of electromagnetic radiation is actually absorbed by the group, and generally there are certain rules that which group actually absorb which kind of electromagnetic radiation, and from there will be able to tell that yes, this functional group is actually present in the molecule. Now, one thing is there, that number of vibrational degrees of freedom for a linear and a non-linear molecule. Okay, this you can derive using that. If suppose if you have an n atomic molecule, okay, if you have any n atomic molecule, so it can move in three directions, x, y, z. So it will have if 3 molecules total are number of 3n number of different degrees of freedom are present in the molecule. From that, 3 will be due to translational, 3 will be translational. It can move in either of x, y, z direction. Rotational, it is actually different. Okay, I am writing here. Rotational, this will be different for linear and non-linear molecule, because in case of linear molecule, one rotation will be like that, it will rotate in the plane. Okay, if non-linear planar molecule, sorry, in case of linear molecule, when it is in a present in a plane, when it is rotating in the plane, you will see there is no change in the structure. So that rotation is not counted. And here for linear molecule, you will have only 2 modes of rotation, and for non-linear molecule, you have 3 modes of rotation. So if you have 3 translation and 2 for linear molecule, if you have 3 translation and 2 rotation, and you have total 3n number of degrees of freedom, so you can identify that 3n minus 3 plus 2, that is 3n minus 5, will be the number of vibrational degrees of freedom. Vibrational degrees of freedom I am talking about here, that 3n minus 5 will be the vibrational degrees of freedom for a linear molecule. And in case of non-linear molecule, since you are seeing that there is, along with this 3 translational motion, there will be 3 rotational motion. So the remaining 3n minus 6, this number of motion will be for non-linear molecule. Now we come to normal modes of CO2 and water. Yeah. So normal modes for CO2 and water we are seeing here. So why these 2 examples are generally chosen? If you search any kind of spectroscopic textbooks where there is a discussion on infrared spectroscopy, or in some books there is vibrational spectroscopy, you will see these 2 examples are generally chosen. There is one is carbon dioxide and one is water. Okay, why? Because one of them is a linear molecule, both are triatomic. One is a linear molecule, another water is a non-linear molecule. Okay. Here comes the different kinds of normal modes. Okay, so here you can see that the CO symmetrical stretching and there is CO asymmetrical stretching, and 2 types of vibration are 2 types of bending are possible. One is in plane, another is out of plane. But in case of water, you can see that one is symmetrical stretching, another is antisymmetrical stretching, and only one bending is possible. If you are going to calculate that how many number of degrees of freedom is possible for carbon dioxide water, if I am going to calculate, so for carbon dioxide, you see n equals to 3. So total number of degrees of freedom, number of DOF will be 9, 3n. So 3 into 3, that will be 9. Now since carbon dioxide is a linear molecule, you see there is 3 translation plus only 2 rotations will be there. What I have told you about, that only 2 rotational motion will be possible for a linear molecule. So 3 plus 2, this is 5. So how many rest of them will be left for vibration? So 9 minus 5 is equals to 4, and you see there are 4 vibrations are there possible. Okay. And if you go to non-linear water, which is non-linear, this is also n equals to 3. Number of degrees of freedom will be 9, also for water. But here you see that how many number of vibration will be there? 3 translation, 3 rotation, so 6. So vibrational will be 9 minus 6, that will be 3, and you see here only 3 vibrations you are seeing. Okay, so from that you can easily guess that for for water, for any non-linear molecule or for a linear molecule, how many different types of vibrational modes are possible? You can predict that. Next.
So before going to next, can I have a clarification, sir?
Sure, sure. Go on.
But simple molecule like carbon dioxide and water, we can able to clearly predict whether it is linear or non-linear.
Mhm.
In some of the questions which I've seen, I'm from not from a chemistry background, but some questions they've been asked for calculate the number of vibration modes for
Mhm.
certain molecules. If it is
Mhm.
simple, we can understand and use the formula.
Yes.
For the molecule which we are not knowing whether it is linear or non-linear, what is the way we can predict whether it will be a linear or non-linear?
Okay, that's a very good thing. Okay. So generally, chemistry people actually they understand which kind of a linear structure, which is a non-linear structure. But if you are not from chemistry, it's no worry. You know about hybridization,
Yeah,
sp2 sp3.
yeah,
Okay. So if any molecule is suppose there is a benzene in, suppose I give you a structure of benzene.
okay.
Okay. So what is the hybridization of this carbon?
sp2.
sp2. And sp2 carbons are generally in plane. They are in plane. So all the carbons will be in plane. Okay. So it
Okay,
will be a linear molecule.
okay,
In that way, you can predict that what kind of molecule is that if you don't know the structure.
okay.
Okay.
That's fine.
Yeah.
And the one more clarification.
Yes. Yes. Yes.
When you have a carbon dioxide, and finally we get with four different type of modes of vibration.
Right.
How do we confirm that all the vibration modes are active in IR or not?
Okay. So okay, I will come that to that this selection rule. That is something called selection rule. Okay.
Okay,
So in every mode, you will need to see that if there is a change in the dipole moment of the molecule. Okay. I will come to that. That is
yeah,
there if there is a change in the dipole moment, then it will show higher activity.
okay,
Okay.
okay.
Anybody else? Yes. Yes.
Sir, N is number of atoms.
I can hear you clearly.
N is number of atoms, na, sir.
Yes. Yes. Yes.
Okay.
It is the number of atom in atomic molecule. I have written here. Yes. What is the question? Okay. So if stronger the bond, higher is the vibrational frequency, right? So vibrational frequency means that in terms of energy, you can give an idea that what kind of frequency in terms of energy there is proportional to nu, right? Is proportional to nu. So frequency higher means energy higher. So if bond is stronger, you need more energy to break the bond or to vibrate the bond, right? So if bond is very strong, you need very much high energy to to move this bond or to move the atoms in the molecule, right? So if in any case in any IR spectroscopy where I will be talking about today, wherever you will see a very strong bond, you can guess that its vibrational frequency ought to be higher. Okay. Now whatever I was just talking that selection rule for IR transition. So two selection rules are there. One is called cross selection rule, and another is called another is you can say that basic selection rule. Okay. So you if you want to confirm that whether a molecule will be showing IR activity or not, whatever we were just talking about, you have to go through these two rules. Okay. First is the gross selection rule, and then another is the basic selection rule, or normal selection rule. Okay. So can anybody tell me what is the two rules? What are the two rules? Can you tell me what is the gross selection rule? Okay, cross selection rule actually tells that delta mu should be non-zero. Okay, so this is the cross selection rule which actually tells that delta mu should be non-zero. Now, what is delta mu? Delta mu is the change in the dipole moment of a molecule. Okay, so anybody among you know about transition moment integral? You know about transition moment integral? Okay, I will take another page. Nobody? Okay. Suppose you are going to attend any kind of questions that people are going to ask you that what is the selection rule for any spectroscopic transition? What will be the general answer? Any spectroscopic transition.
Sir, energy between two states should be equal to the EMR,
Okay.
the
Suppose
radiation we used. Yes, sir.
is this Prakash?
Yes, sir.
Okay. Suppose these are the energy levels. Okay. Okay. I know you know that vibrational. What is the selection rule for vibration? You know you know. So if the difference are same, right? So all the transitions they are all possible.
No, sir. There is a selection rule that is from the delta n is equal to plus minus 1.
Yeah, but for this case, for I am talking about any spectroscopic transition. One condition you need to satisfy, otherwise no spectroscopic transition will occur. Yes, that is you are correct. That is here. That is what I am just talking about just before. Okay. So what I was talking about that basic selection rule for this case that is delta V equals to plus minus 1. Okay. That means the transition between two states is allowed if they are apart by 1 unit. What I am talking about, suppose these are my levels. Okay. So this is my V equals to 0, V equals to 1, V equals to 2, V equals to 3, and this is suppose V equals to 4. So this transition and this transition and this transition. Okay. Suppose I am naming it A, naming it B, naming it C. Which one is allowed? Is A allowed, B allowed, or C allowed? Which one is allowed and which one is not allowed? Who can tell me? A, B, C. Vibrational transition. All are vibrational levels.
Sir, A is allowed
A is allowed.
in
B.
case of simple harmonic oscillator.
Yes. Yes. Okay. You take this case of simple harmonic oscillator. Yeah. A is allowed. B.
These should not be allowed, sir,
Why?
because here delta n is equal to plus 2. That is two difference.
Exactly. This is not allowed. See.
C
That
is
is
also not allowed, sir.
yes. There is also delta V equals to plus 2. So that is not allowed. Only A1 this is allowed. So this is the basic selection rule or normal selection rule that vibrational transition generally occur between the corresponding states. Okay. It cannot jump from one. It cannot go to any other state without crossing this any one state. Okay. So if you go from if suppose molecule is here, so it has only possibility that it can go either to here or either to here. Okay, so this is the basic selection rule. I am talking about now gross selection rule, where I have told you just that there should be a change in the dipole moment. But my question is, for any spectroscopic transition, whether it is IR, whether it is rotational, any spectroscopic transition, vibrational, rotational, anything, anyone, there is a general condition. What is that condition? I am just want to know that.
Sir, is it population ratio?
Population ratio actually detects sensitivity. Okay, like population difference occurs for NMR, population difference occurs for vibration also, but the two processes are actually different by sensitivity.
The frequency should be equal to the energy transition level. Means
Yeah, that you were talking about. This is the resonance condition. So if I give this much energy, understand this. This is a very interesting thing. If I can give this much of energy, will this transition happen? You are giving this much energy. Suppose you are giving equal amount of energy of A. Okay, this transition is happening. If I give same energy corresponding to B, will the transition of B from B equal to 0 to B equal to 2 will happen? Are you getting my question?
sir, are you saying that from ground state to the second state, or from ground state to first state?
Excited state. This is the second state called excited state. Yeah.
So then it should generally occur, means from ground state to the second state, if the frequency is same. Means
That means if what you are saying, if that is the case, then there will be no selection rule. There you have selection rule plus minus one. In every transition will happen, just like if in case of Morse oscillator or what you known as anharmonic oscillator. In that case, all transitions are allowed. Is that the case? Yeah. Okay. Okay, I'm answering that. So, if you know transition moment integral, okay, first giving this answer to this question, whatever I have told, that if I give energy equals to A, will it happen? If I give energy equals to B, will it happen? Yet it will happen. Always it will happen. But probability will be less. Probability will be less. So in spectroscopy, forbidden doesn't mean that it doesn't happen. Okay, but it happens with very less probability. Now, if I coming to this transition moment integral, if this is my state M, this is my state N, if wave function corresponding to state this is psi M, if wave function corresponding to this state is psi N, so if you see in the spectroscopic transition, do you know by bracket notation? How many of you know by bracket notation?
Sir, I have read this in quantum mechanics, but I
Yes,
have
yes.
forgotten. There is
You know-
something bra and Kate notation.
Yes,
behind
yes,
it.
yes. Brand Kate notation, right? Okay. If you don't know, it's always possible. No problem. If you don't know, it's no problem. Okay, so I cannot rewrite that. Okay, fine. So give this integration, all of you know. If this is the case, psi n star mu psi m. Okay. If you go through that what kind of transition it will be possible, if any transition is possible, you need to calculate quantum mechanically, you need to calculate this one, which is also known as transition moment integral. Okay, if you have learned basic quantum mechanics, you will learn that, or if you have not learned, you will learn later. But for now case, you understand that this is called transition moment integral. It is written like this. So for any spectroscopic transition, before going to any selection rule, you must be knowing that your transition moment integral should be non-zero. Okay, your transition moment integral, that should be non-zero. In this case, you see, to make it non-zero, you always need this mu to be non-zero. This is essential. Okay, this is very much essential, that your mu should be non-zero. If you want to see any derivation, you can refer to any kind of quantum mechanical books where you will see the derivation. But for now case, you see that for make it transition dipole moment non-zero, you see that your mu, that is change in the dipole moment, it will be non-zero. So in this case, the gross selection rule actually establishes that there should be a change in the dipole moment. Otherwise, what will happen if transition moment integral, this will be zero? Yes, somebody wants to say something? No.
Hello.
Yeah.
So there was a connectivity problem in
Should I
follow
repeat?
the selection rules. Only just kindly brief both of them.
Okay. Do you know about transition moment integral?
No. I when the connectivity was lost, you were starting with that cross selection rule. So from that onwards.
Oh, you have not seen that on?
No, because there was some connection problem. So
Okay.
sorry for that.
Okay, yes, it's okay. So if you have two states, suppose M and N, and there is suppose this is the wave function corresponding to M, and this is the wave function corresponding to N. So for any spectroscopic transition, you need that your transition moment integral, that should be non-zero. Okay. So if you want to know that what kind of spectroscopy it is, before going to any selection rule about among these principal quantum numbers, that delta V, delta R, or delta N, what you will be, before going to that, your first thing will be that for any spectroscopic transition, your transition moment integral, that part should be non-zero. Okay. So now, if you want to see any kind of derivation, you can see it in any kind of spectroscopic books. But for now, you see, this is the transition moment integral expression. Now, these two states, if you this will be too much quantum mechanics. Okay, so this state up to now, you just understand that to make it non-zero, you need this one must be non-zero. Okay, so there should be a change in the dipole moment. That was I am talking about, that in the gross selection rule actually tells that your dipole moment should also change. First main selection rule is this one, that if you want to see that any kind of vibrational transition is happening or not, you need to see that yes, if your dipole moment is changing or not, and then you need to see your basic selection rule, that is delta V equal to plus minus 1. But this is also what Prakash has said, this is also only applicable for harmonic oscillator. If you go to harmonic oscillator approximation. If you go to anharmonic oscillator approximation, delta V equal to plus minus 1, plus minus 2, plus minus 3, all are becoming allowed. Okay. Now, coming to these three or four different things: overtones, combination bands, difference bands, and Fermi resonance. First, coming to overtone is nothing but whatever transition you are seeing for any molecule, this is called fundamental transitions. I think you have learned about that. That whatever transition you are seeing in a molecule, it is nothing but a fundamental transition. If any transition happens with energy equals to double of the fundamental transition, suppose my fundamental transition is happening with an energy, x, and if you see any weak band corresponding to 2x, 3x, 4x centimeter inverse, I should write this unit, this centimeter inverse, then these bands are generally called overtone. Okay. In some cases, it may happen that two different vibrations, they are actually getting coupled, and this combination band will have frequency more than that, and they will add up. The frequency will generally add up. This is called combination band. And if they get subtracted, they will be difference band. But it is very rarely seen, these two bands. And also there is something which is called Fermi resonance. That is the coupling, where I have talked about this difference and combination band. It is nothing but a coupling. In case of combination band, they all add up, but in case of difference band, they are just getting subtracted. In case of Fermi resonance, the same coupling occur, but one is overtone, another is or combination band, or another is fundamental one. Okay. So this, if combination between this overtone and fundamental one, this combination happen, this is known as generally Fermi resonance. But in general cases, in general IR spectra, you will very less see these kind of bands. Now, coming to next discussion, that two types of IR spectrometer. Professor Shankar Raman has discussed that one is a dispersive type IR, where you have a chopper, and using this chopper, you just monitor what kind of light will pass. That is from the reference of the reference and or from sample, you can confirm. Or one thing is Fourier transform IR, which is used using this Michelson's interferometer. You have seen that one is movable mirror is there, and it will move, and it will give you that what kind of frequency it is giving, and from this Fourier transform, this frequency will be converted to this time, where we will see that this transformation, that is the arc-free IR spectra, you will get, and from that you will be able to identify what kind of groups are present in the molecule. Now you need to calibrate. Okay, so whenever you are buying any kind of IR spectrum instrument, you first need to calibrate the instrument. So to calibrate anything you need to calibrate, you need something it is already known. You just need to match that. What is that? In this case, it is generally a film of polystyrene. It generally gives two peaks at 1630 and 3062 centimeter inverse. So you make just a film of polystyrene, you just put it in the IR spectrometer, you just record the IR spectrum, and you just calibrate that where it is coming. Okay. From that, you can, if you can calibrate this one, and then you can record your spectrum of interest. Now, sampling techniques in IR spectroscopy. This is already taught by Professor Shankar Raman, that what kind of sampling is used generally. For gas sample, there is a NaCl kind of what you say. This NaCl kind of stopper kind of thing will be there from the, because the NaCl, CSF, these kind of things are generally used. Can anyone tell me why these kinds of things are used? NaCl, CSF, KBr, etc. These kinds of are generally used for, if you have solid sample, you need to make the palette with it. If you have liquid sample, you have to put between two NaCl plates. Okay, these plates, yeah, NaCl plates. But why these compounds are used generally for IR sampling? Can anybody tell me? It is a very basic question.
It's highly transparent to IR.
Highly
transparent to infrared radiation.
Another one, any idea? Another
That means
transparent.
it will allow all the light, whatever comes in, it will be passed on to the sample. That is why.
Why it will not absorb?
They won't observe the IR spectrum, the range of IR.
What one? Which one? I can't hear you. What do you say?
These molecules won't observe in that region.
Okay. Anybody else?
So these are ionic compounds,
Exactly.
and they break into ions, so they does not absorb IR radiation. There is no bond.
Exactly. So in IR, you are just looking at that bond vibration, right? So you need something which don't have any bond. NaCl has very less chance of any kind of bond because they are very much ionic. NaCl, CSF, KBr, etc. That's why people generally use these kind of things for sampling of IR spectra. They can be easily mixed with the solid sample of interest, and if you can make palette of it, you can then record the IR spectra, because these compounds will not absorb any kind of IR radiation. Now, if you have any alcohol sample, you will see the strong and broad with stretching band at 34,000 to 33,000 due to hydrogen bonding. Okay. So if you have any kind of strong and broad peak at 4,000 to 33,000 in the IR spectrum, you will be able to tell that hydrogen bonding wedge is present. Now, intermolecular and intramolecular hydrogen bonding, you can differentiate between them effect of dilution using the effect of dilution. Suppose okay, this is the shocker. Which one is intermolecular hydrogen bonding and which one is intramolecular hydrogen bonding? Suppose case 1, I am naming it. This is case 2. So one is intra or inter?
One is intra.
One is intra. Intramolecular hydrogen bonding. Right? That means for intramolecular hydrogen bonding, the hydrogen bonding will happen within the molecule, okay? But for intermolecular hydrogen bonding, these two hydrogen bonding teams that will be from different molecules. Here H from one and Cl from one. H from one and Cl from one. Okay. Now you have given, suppose you have given, this is, what is this? This is orthochlorophenol. Okay. Orthochlorophenol. And this is parachlorophenol. Suppose you are given, you have been told that there is two container, one there in one there is orthochlorophenol, in another there is parachlorophenol. Okay, you need to distinguish which one of these is ortho and which one of this para by only using IR spectroscopy. How will you do that? Yes.
Upon dilution, the intramolecular bonding won't break, whereas intermolecular will undergo breaking of the bonds.
Yes, because the molecules will go apart. Okay. Yes. So if you just do dilution, very simple thing. You just do dilution. What will happen? This hydrogen bonding, which is within a molecule, if you take only one molecule of it, you will show a hydrogen bonding, right? So dilution will have no effect. But here you will see that if you increase dilution, what will happen? The molecules will not come close enough to form more hydrogen bonding. So we will see the hydrogen bonding will be lost and change of weight stretching frequency. So you just take one sample, you just do dilution and check IR. If you see any kind of change, then you can say this is parachlorophenol. If you see don't any change, if you see no change, you will confirm that this is nothing but orthochlorophenol. Now there is something which is distinguishing this primary, secondary, and tertiary amine based on your structure. Suppose you inform NMR, you and mass, you got that you got some primary amine or some secondary amine or some tertiary amine. Now we need to confirm that whether it is exactly the secondary, primary, or tertiary amine or not. How will you say? It's very simple. For primary amine, you see the three difference by only one thing, NH2, the for primary amine. For secondary amine, this will be NH, their group, and for tertiary amine, there will be no hydrogen. Okay. So for this one, for primary amine, you will see two bands corresponds to NH2. This will go symmetric stretching, this anti-symmetric stretching, you will see two bands. For NH, only one bond is possible, only one band. And for tertiary, there is no hydrogen, so you will not see any kind of NH stretching frequency. Okay. By that means, you will be able to tell that whether primary or secondary or tertiary amine is present in the molecule. Now, coming to carbonyl. Okay, this is a very vital thing which is very much used to identify from this IR spectra that which kind of molecule is present in the which kind of groups are present in the molecule. And one of the main thing that if you suspect any kind of carbonyl moiety is present within the molecule from your NMR data and your mass data, you need to confirm that if yes, carbonyl is present, the IR is a very good way to tell that carbonyl is present. Okay. And also this value of this carbonyl stretching is dependent upon which kind of group is attached to. What I am saying, carbonyl okay, so which kind of groups are present in these two bonds, they actually dictates what will be the frequency of this carbonyl. You can see this list I have taken that the substituents which is attached here, suppose I am naming it A, suppose I am naming it B, B, suppose. So what is A and what is B, is it electron donating or electron withdrawing? This will completely dictate that what kind of vibration it will show and what will be your position. And you see its position can be changed from 1690 to 1810, right? The position can be changed to 100 centimeter inverse. Okay. Now, effect of the ring size on carbonyl stretching frequency. This I will not talk about now. I will solve a question, then you will be able to understand, and I will discuss that again. Okay, effect of alpha halogen substitution on the carbonyl stretching frequency. That is, suppose the cyclohexane is here. So which of these will have higher dipole moment? One or two? This is axial and this is equatorial. Which will have higher dipole moment?
Axial.
Axial will have higher dipole moment. This is one dipole. This is another dipole. Now I think we will be able to tell. Which one will have higher dipole moment?
Sir, 2.
2. Exactly. Because this will add up. This is in the same direction. And here you can see this is somewhat cancelling this moment. Okay. So always dipole moment of 2 will be always greater than 1. Okay. So since dipole moment is different for any alpha substitution, so for alpha halogen substitution for any group which is axial or equatorial, this will dictate that what kind of stretching frequency we'll see in the molecule. Okay, so in nitro, for the case of nitro, this is the structure of nitro group, right? And this oxygen lone pair, this is another resonating structure. You will see. Here then it will be double bond O, but both are equivalent, right? Both are nitro. So two bands you will see only for nitro in stretching. That one is symmetric stretching. Where what is symmetric stretching? You stretch these 2 bonds, okay? And since nitro is a non-linear, so if you will stretch it, then n position of n will be moved. Why it will move? Because since it is a non-linear molecule, to make this center of gravity is constant, it will need to move in any direction, okay? So dipole moment will change, and in asymmetric mode, you just give unequal movement, okay? So symmetric one will be there, another one will be asymmetric mode. So if any nitro compound, you have any nitro compound in the IR spectra, we will see 2 modes, and this symmetric generally, which one will be higher energy, symmetric or asymmetric? Which one will have higher energy, asymmetric or asymmetric?
Symmetric.
Symmetric will have higher energy. Okay, you symmetrically just pushing some, suppose you have some bond like this, you are symmetrically pushing like this, okay, equally. And you need to do it for more like this, okay, unequal. So which one will have you need to use more energy, equally or unequally?
Unequally, sir.
Exactly. So for asymmetric stretching, you need more energy, and it generally comes near 15,000 or 1550 or 60, 1560 like that. And this one generally comes near 13,000 or 1350 like centimeter inverse. All are in centimeter inverse. Okay. Now differentiating cis and trans 3-hexane 1-all based on IR spectra. This is well described by Professor Shankar Raman that in case of cis and trans, your dipole moment will be different. In case of cis, the 2 groups will be oriented like this, and in case of trans, if you can follow my fingers, in cis there will be like this. These 2 groups will be like this. In trans, they will be like this. Similar to the case of the cyclohexane, what I have shown you here, the vibrational, the dipole moment will be different for cis and trans. Since dipole moment will be different, you will see there will be change in the IR spectra. Okay, from that you can understand it, that, and you can differentiate that cis and trans 3-hexane 1-all. Okay, so these are the things that I have discussed. And also Professor Shankar Raman has explained very well. He has taken very good examples to discuss all these things. Okay, so now going to the questions. Okay, so this is the first question. You need to arrange the following in the increasing order of energy of the vibrational frequency. So these 3 questions are here. Okay, so okay, so this is the first one. You need to compare. Yeah, this is the first one. This is the second one, and this is the third one. You need to compare here these 2 carbon, which is both sp3. Here carbon oxygen, sp3 carbon oxygen, sp3 carbon nitrogen, sp3 carbon bromine. And you need to follow that what should be the order of this CX bond vibration. Here in the second question, you need to hear it is again written B, but you need to compare these 2. This is sp carbon hydrogen, sp2 carbon hydrogen, sp3 carbon hydrogen, and you need to follow what is the CH vibration. Here you also need to see that CC, C double bond C, and C triple bond C, single bond, double bond, triple bond. What will be the order? Okay, so you just do it, and I'm just coming. Aha. Sorry guys for the delay. Okay. So yeah, what should be the answer? The first one. Okay, we will go one by one.
Sir, A greater than B greater than C greater than D.
Okay, just you tell me which one will be higher.
sp3cc will be higher than sp3co, then sp3cn, then sp3cbr. For the first question A.
For the question A, you are saying that CC will be greater than CO, right?
Yes, sir.
This one,
Sorry, sir, my mistake. Carbon bromine bond would be least value because bromine has higher mass,
then
so the bond strength will be lower. So the vibration frequency will be lowest for CBr. And carbon, nitrogen, oxygen. Carbon, nitrogen, oxygen. Carbon will be the highest.
carbon will be the highest.
Yes, the CC will be the highest. And then CN from right,
CN.
and in between CO.
Anybody else?
Yes, sir.
Which one? Anybody else?
Yes, sir.
Are you, there is so much of
Hello. Carbon, bromine, carbon, 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 nitrogen, then carbonyl.
decreasing or increasing.
Carbon, bromine, I think 500 to 700 centimeter inverse. Carbon, carbon, 900. Carbonyl, 1215 to 1100, I think.
So which one will be lower? Carbon bromine will be lower. Then
500 to 1700 centimeter inverse. Sir.
so which will be just you need to tell qualitatively higher and lower. Which one will be higher? And what is the concept?
Higher, sir, higher.
That will be for okay. Okay, let me discuss this. So first thing is that the vibrational frequency you know this Hooke's law, as nu is nothing but 1 by 2 pi root over k by mu, right? Right, this one. So this mu, this 1 by 2 pi is constant. So it depends upon two factors. One is k and one is mu. So nu is generally proportional to k, and this nu is proportional to 1 by mu. Right? You can see here. Now you see what I have written here, that mu is directly proportional to force constant, inversely proportional to the reduced mass. Okay. Now the first thing comes that these four you need to find that Cx bond vibration. Okay. So here major factor will be mu. Why mu? Because mu is the reduced mass. Okay. And what is K? K is the bond strength. So in these four cases, I know bond strength is different, but significant effect will be observed for this mu. Okay. Now you need to find that you need to arrange these among these following in the increasing order. That is, you first need to find which one will be the lowest. So mu will be lowest for which, nu will be lowest for which mu will be highest. Okay, nu lowest this is mu, and mu will be highest. Now, among these four, you need to find which one have higher mu. So you see that highest molecular weight is of bromine, right? Since bromine has highest molecular weight, so your reduced mass will be highest for CBr. Since CBr has the highest molecular weight or highest reduced mass, so it will have lower vibrational frequency. Okay, so first thing is the CBr. Now you need to find the other three. Among the other three, which one will have higher molecular weight? Carbon, oxygen, nitrogen. You know this is oxygen. So this is oxygen. This is nitrogen then, and then this is carbon. You see, this is the answer. Okay, first will be CBr, which will have higher mu, that is reduced mass, which corresponds to lower vibrational frequency. Second will be carbon oxygen bond. Third will be CN, and fourth will be CC bond. Now about the second one, which one will be the second one?
Sir, sp3ch would be the least, then sp2ch, then spch.
Yeah, what do you say? sp3 ch
sp3ch would be the least, then sp2ch, then spch.
Why?
So due to hybridization,
What will happen due to hybridization?
sp hybridization, that means more percentage S character, which means more bond strength. So it would be higher vibrational frequency.
Exactly. Very good. Okay. So this case, you see, in this case, you cannot compare your mu. Why you cannot compare? Because in both three cases, you will have only C and H, carbon and hydrogen. The mu will be same. So how will you then compare? You will compare using K, your bond strength here. Okay. So need to find which bond is whatever I told you, that stronger the bond, higher will be the vibrational frequency. Now in this case, you see in bond how many percentage of S character is there? 25%. Here 33. So higher S character means bond is more stronger. Okay. So you cannot remove hydrogen. It is very difficult for removing hydrogen from any sp carbon. Okay. So you will see generally that since it is very much stronger, so it will have higher vibrational frequency compared to the other two. Okay, so this is the perfect order that you told. sp3 CH less than sp2 CH less than spch. Okay. Now coming to the last one, C single bond, double bond, triple bond. Which one will have higher frequency and which one will be the least?
C triple bond will have highest.
C triple bond.
C triple bond, then C double bond, then C single bond.
Higher will be which one?
C triple bond, sir. One strength will be more.
Exactly. Same result. Single bond, double bond, triple bond. You need no triple bond is very much stronger. You get to it is cool. Very much stronger triple bond. So it will be have higher energy. In terms of hybridization, you can again say that it will have higher energy. Okay, fine. I'm going to the next question. C triple bond C stretching band of internal alkynes are generally absent, very weak in the IS spectrum in comparison to C triple bond C stretching of terminal alkynes. What is saying? That suppose you have two alkynes. First case, suppose I am writing is the second case. Okay, suppose you have one alkyne like this. Okay, and you have another alkyne like, okay, so what is the difference? Suppose I am writing it R. In here, 1 R, here 1 R. So what you need to compare? You need to compare C double triple bond C. Which one will have higher stretching or which one will have a lower stretching? You need to compare. But one information is given that for which one is internal alkyne, this one is internal alkyne, right? Because it is present within the bond, within the molecule bond. Okay, internal alkyne, because it is no hydrogen attached to this alkyne, and it is called terminal alkyne. Okay, this is the terminologies. This is called terminal alkyne because this carbon hydrogen is attached here. So this is called terminal alkyne and this is called internal alkyne. Now you need to compare the C triple bond C stretching. What is saying that for internal alkyne, this is for 2, this case the stretching bands are generally acid or very weak. Sorry, very weak in the IR spectrum in comparison to C triple bond C stretching of terminal alkyne. So what could be the reason that for this one, for 2, this IR stretching weak or absent? But for here, 1 is present. For mainly the reason that for why for internal alkynes, the IR stretching is generally absent or it is coming very, very weak. What could be the reason?
Is this due to plus I effect of the alkyl groups in internal alkyne?
What will happen then?
Sir, plus I effect will decrease the bond strength between C triple bond C.
How plus I effect will decrease? Plus I effect means?
Sir, electron density towards any atom.
Electron density donating or electron density withdrawing?
Sir, plus I effect donating.
Donating. So if you donate any electron to any bond, will the bond strength increase or decrease?
It will depend, sir, whether the where the electron are going, anti-bonding orbital or bonding orbital.
Suppose you have a group which is have plus I effect and it is attached to a double bond or it is attached to a triple bond. So in which case the bond strength will be stronger?
No idea, sir.
If you have any plus I effect group, that means it is pushing electron densities. In general case, if I am not considering this MO diagram, in general case, if any group is attached, if it is pushing electron density, then it will increase the electron density, and increase the electron density means the bond will be very stronger, right? C triple bond, why it is very stronger? Because it has more electron density compared to double bond, right?
Yes, sir.
Right?
Yes.
If the electron density will be higher, then it will be more peak, like that.
There is no polarization in the internal alkynes, and hence they are weaker and then absent in the absorption bands.
Which one? Internal
In case of internal alkynes, there is no polarization. The molecule behaves as totally non-polar, and hence there was no intense absorption bands in internal alkynes. Whereas in terminal alkynes, there will be polarization, and hence you can have intense signals.
How can you call it a non-polar? Any terminal internal alkyne?
Is it because of the molecular symmetry?
Yes. But it really depends, because what kind of groups R is, that depends completely that which kind of polarity it will possess. But exactly the answer is correct. This is very much more symmetric. So this is the answer. That for internal alkyne, due to almost symmetrical nature, their dipole moment change is very less. Okay, but for here the dipole moment change is very much high, because the two groups actually in this case the symmetry is very much broken. Okay, if these two groups are different, R and R prime, what we will see? Dipole moment will see them? No. But the difference, if there is some group, and this difference will be very much different. Okay, so this is much more symmetrical nature. So for this terminal alkyne, dipole moment change will be less. So less change in dipole moment. So what will happen if there is very less change in the dipole moment? What I have told you, very less change means very weak band. That is what is asked in the question. That very weak band are generally absent in the IR spectrum, but in case of unsymmetrical one, there is huge change of the dipole moment, which gives a strong peak in the IR spectrum. Okay, this is the logic that in case of symmetric, in case of terminal alkyne, they are very much unsymmetric, whereas for internal alkyne, they are very much more symmetric. Since they are very much more symmetric, the dipole moment change will be very less. So this is the reason that they will be show very weak band or very sometimes they are very absent from the higher spectrum. Yeah. Now going to the next question, that functional groups such as anhydride, carboxylate, not carboxylic acid, nitro primary amino group, they give two stretching vibrational modes in the IR spectrum. This is very easy question. What is the origin of these two bands? Two stretching bands. What could be the origin?
Symmetric and asymmetric.
Exactly. Symmetric and asymmetric stretching. All of these will show two different types of stretching. One is symmetric stretching and another is asymmetric stretching. It's a simple, straightforward question. Okay. Now, coming to this question. As the ring size increases from cyclopropane to cyclohexanone, the carbonyl stretching frequency decreases. You need to explain the observation. I am just writing the structures. Okay, so I'm not writing drawing the chair form. Okay, then, okay. For your comparison. For this cyclopropane, this value is 18-15 centimeter inverse. For cyclohexanone, so cyclopropanone, this is 18-15 centimeter inverse. For cyclohexanone, this is 17-15 centimeter. Suppose this data is given, and if suppose in some cases they in between, generally given in between the cyclobutanone like this or cyclopentanone. In between generally they comes between 18-15 and 17-15, but this is seen as the ring size gradually increases, the vibrational frequency decreases. In other words, I can say that if you go from cyclohexanone to cyclopropanone, as your ring size decreases, your vibrational frequency of carbonyl increases. What could be the reason? Who can tell me? Which decrease in ring size, vibrational frequency of the carbonyl increases. What could be the possible reason?
Sir, due to the bond strength, C double bond O, because inside the ring the bond angle is decreasing. That means outside the ring bond angle is increasing, and more the bond angle, more percentage S character, and more stronger the bond.
More the bond
Is this
angle?
correct? Sir, as we move from cyclopropane to cyclohexanone, sir,
Bond
inside
angle
the
increasing?
yes sir, bond angle outside the ring in cyclopropane, bond angle outside the ring is highest. That means percentage S character is highest.
Bond angle outside the ring, that was don't have any meaning. Bond angle is this one. This is the bond
Because of angle strain.
angle strain. What will happen? What will happen because of angle strain?
S character is increased.
Which one?
Due to angle strain, S character is increased of that carbon.
How? Yes, whatever you are
Sir,
correct.
sir,
Yes.
inside the ring there is low bond angle in cyclopropanol.
Okay, I'm
That
writing.
means
Okay, wait, focus. Here it is 60 degree.
yes, sir.
Suppose in butanol it is 90 degree. No.
Yes, sir. In cyclopropanol, there is a less bond angle. That means percentage S character in that carbon-carbon bond is less.
Yes.
So the rest percentage S character goes up to the carbonyl bond, C double bond O, which makes it stronger.
Exactly.
Yes,
Correct.
that's why it has higher.
Correct. So whatever he has said that if you increase in ring size, okay, increasing ring size, the carbonyl stretching frequency decreases. Why? Because suppose you go from here to here, what will be the hybridization of this carbon? This is sp2, right? Carbonyl carbon. This is sp2 hybridization. So you need sp2 ka what will be the bond angle for sp2?
120.
120. Now when you are making any 120 carbon bond angle, you are making it to 60 degree. Okay. So the strain is developed in the molecule. This is also known, some people have mentioned, this is known as angle strain. Okay. So if you are making a 120 degree bond angle molecule, you are making it to 60 degree. So you will generally develop any angle strain. So what will happen? This will increase your P character or P character of the bond will be more involved to minimize or to compensate this angle strain. Okay. Because the bonds, the P character of the bond is generally used, this actually dictates that what kind of bond angle will be there, right? This sp2, sp3, any kind of thing, this P is actually dictates that what kind of bond angle will be there. So P character will dictate that, and since you are generating angle strain in your molecule, so P character will be much more involved with the bonds. So what will happen? So more S character will be here. Okay. You have some S and P, you are giving P to somewhere else, so what will happen to S? S will go to the next one, so S will go to the carbonyl one. Now, in a bond, suppose carbonyl, if you increase S character, what will happen? Bond becomes stronger. More electron density, bond becomes stronger. The bonds become stronger, what will happen? By new increase. Bond stronger means K increases. K increases means new increases. New increases means you will see higher vibrational frequency, and that's what you are seeing for very strained rings where more angle strain is there compared to this one. Okay. This is the reason that if you go from cyclopropanone to cyclohexanone, your angle strain is actually getting released. So the carbonyl bond is the S character of the carbonyl bond is getting decreased. And since S character is getting decreased, the bonds become very weak, and so you will see there is an decrease in the carbonyl stretching. Whatever you have seen here. Okay. Fine. Now, the very straightforward question that what evidence IR spectrum can provide concerning the existence of penta 2,4 dione in the enol form. Okay. So you have this one. Okay. What is the name of this compound? Okay. One thing. So what is the name of the compound? It's called AC. Okay. If you go to, this is not air condition. If you go to any studying chemistry, people will say that ACAC like thing. Okay. So ACAC doesn't mean 1 1. ACAC means this one, AC. Okay. And now what this stands for AC? AC is nothing but acetyl acetone is in short form. It is generally known as ACAC. Okay. AC. Right. Acetyl acetone. Okay. Now this group is called acetyl acetone. So if you have read tautomerism, you will be able to tell me that this arrow, which side it will be bigger and which side it will be smaller. From left to right, it will be bigger or smaller. Understanding my question? I am saying that this acetyl acetone in general will exist in which of these forms? This form or this form? If it exists in this form, so this to this arrow will be higher. Okay, suppose I am saying this one, it will be this one or this one. If this is more feasible one, suppose I am naming it 1, if this I am naming it 2. Understand? Then first understand the question. This is 1, this is 2. If 1 is more stable than 2, that means molecular equilibrium will be shifted to that side. So then it will be the correct arrow. But if this is more stable, then most of the molecule will go to that state and this will go like this. So which one will be more favored? This one, first one or second one?
Sir, I think second one.
Second one. Why?
Due to hydrogen bonding and forming 6-membered ring like that.
So which one will be stable?
Second one.
Okay. Okay, you are saying that this one will be more stable. Yeah, this
Yes, sir.
equilibrium will follow. Which one you are saying?
First one, sir. First equilibrium.
First equilibrium followed. Do you know how much percentage this on generally? Yes. Someone is getting something. Okay, do you know how much percentage is the form? I mean, if you start with 100%, how many of this will be in this form?
No, sir. No idea.
Okay.
But
About
generally, yes, sir. Generally, enol form. Generally, enol forms to greater extent, but here I think first equilibrium should be the right answer. Yes, sir. You are saying right 90%. Yes, sir.
Yes, it's almost 90%. It is almost 10%. So mostly this structure will be very much predominant. So I am writing clearly this structure here. So if you have acetyl acetone, it will quickly convert to this one. Since this is more stable than this one, so equilibrium will be that sided. So this will be the correct arrow. This will be small and this much will be higher. So most of them will be converted. And now why they will convert? Because they will be stabilized by 6-membered ring and intramolecular hydrogen bonding. Intramolecular H bonding forming a 6-member transition state or 6-member ring. Okay. Now, question is, what evidence IR spectrum can provide concerning the existence of penta 2,4 dione in enol form? That means I am saying that this is the more prominent form, which is the enol form, right? Ketoenol tautomerism is enol form. So, if in compound has in enol form, how can you prove from your IR spectrum? This is the question. How can you prove?
So there will be an OH stretching frequency in the second one.
OH stretching frequency. Good, correct. We will be the sharp or broad. Yes, what you are saying, OH stretching frequency, right? Okay, so it will be sharp or broad.
I'm not sure, sir.
Okay, so when OH is sharp and when OH is broad. Remember what I have told you? If OH is
Dick
hydrogen
proton.
bonded, yes. Someone is saying something.
Is Dick proton shows a broad spectrum.
Yes, if it is hydrogen bonded OH, then it will show broad spectrum. If it is not hydrogen bonded, it will show short spectrum. Right? Now, here you see this. Why? What about this OH? This is hydrogen bonded, so it will show broad spectrum. What is the approximate region of this stretching? Where you will see approximate.
Sir, 3400 to 3200.
Yeah, that region, 3400, almost. Yeah. And only OH.
3600.
No. I mean, what I'm asking, that only OH you will see or any other thing?
There will
Carbon
be a
double bond.
carbon. Yes, sir. Carbon.
Carbon double bond is also possible. Carbon double bond. Another. See, generally this carbon double bond and carbon oxygen double bond, they generally come very closer. Okay, 16,000, 17,000. You have seen that. So
Carbon oxygen stretching.
yes, that is a very vital thing. That one I was just waiting to hear. It's carbon oxygen stretching. Why? Because here this way carbon oxygen bonding, it is hydrogen bonded, right? Since it is hydrogen bonded, you will see a change in the stretching frequency. So how if carbon oxygen is hydrogen bonded, what should be the frequency of carbon oxygen? Carbonyl frequency, where it should come if it is hydrogen bonded? This generally comes 17,000, suppose 17,050, almost. So if it is hydrogen bonded, then where it will come? Go to 18,000 or 16,000. That was it is enough. बोलो कुछ बोलो. Will it increase or decrease carbonyl stretching frequency if hydrogen bonding is there?
Decreases.
Right? The more electron density is here, if carbonyl in the electron density is actually shared with hydrogen. Okay, hydrogen is taking that. It is hydrogen bonded, so it is taking something. So it will reduce its strain. So it will reduce its strain means it will decrease the vibrational stretching frequency. It will come nearly 16,000 or 1650 kind of thing. Okay, in this range you will see carbonyl, which is hydrogen bonded, and exactly this is the way you can predict that the IS spectrum will show a broad band nearly 3,000 or 3,400, whichever is centimeter inverse, due to hydrogen bonded nature, and also a shift in the CO stretching, which is not present here. Here CO is not hydrogen bonded, so you will see here the 17,000 kind of 1750 kind of thing, and here you will see that this one will be of 1640 or 1650 kind of thing. So from this shift, you can really understand that which form is actually existing. So also from C double bond C stretching frequency, you can also get an idea. Okay. Okay. Another straightforward question: infrared spectrum of an alcohol measured at as such, that means a neat sample. This showed OH stretching as a broad band. Okay, so I'm taking an alcohol ROH. Okay, it is showing a broad band at 3000 centimeter inverse. Oh, sorry, 3300. Whereas a dilute solution chloroform showing OH stretching about 36,000 centimeter inverse, and also it is sharp. So what could be the reason? Can anyone tell me? Very basic question. Sorry. Can anyone tell me what is the reason? What could be the reason?
There is no hydrogen bonding in the diluted solution.
Yes. So that will be hydrogen bonding, which is what kind of hydrogen bonding? This is
Intermolecular.
yeah, intermolecular. Okay. So intermolecular hydrogen bonding is actually getting perturbed if you have need solution, and if you have diluted it with toluene, you will see there is a shift of this OH stretching frequency. Now, since in dilute solution OH stretching, the OH bond is not hydrogen bonded, so it is not sharing its electron density. So electron density is confined within OH. If hydrogen is bonded to someone else, so some molecule, some electron will be transferred there. Suppose that. Okay. So if OH will be able, suppose if some X is there. Okay. So yeah. So it is hydrogen bond is some X. Suppose this bond electron density will be held by this one to bond with this one. So this will be very weak, right? Since this will be very weak, so intensity will be, so its vibrational frequency will be low. But in dilute solution, its no hydrogen bonding is there. It will always get its own strain. Since it will get its own strain, so it will have higher vibrational frequency. Okay, and it will show sharp band. Okay, so this is the answer, that there is the explain of the observation is here to explain that there is the presence of intermolecular H bonding. Okay. Okay. Carbonyl stretching frequency of the compounds A and B are shown below. Explain why compound B has lower carbonyl stretching frequency. I think now how much I have discussed about carbonyl stretching, you will be able to answer that. What was the answer?
Hydrogen bond.
Because of hydrogen bonding,
In which case?
B structure.
B. So I write it like this. Okay, so this is the hydrogen bonding. So in this case, suppose this is case B and case A is there. Case A is there, where there is CO, C, and here there is no hydrogen bonding. A, right? So hence hydrogen bonding is there. So suppose it will take some electron density from here. So what will happen? This CO bond strength will decrease. Since CO bond strength will decrease, the vibrational frequency will decrease. And that is seen for B, that your vibrational frequency is getting decreased. So hydrogen bonding is generally possible for B, whereas it is impossible, or it is possible for A. That is also a very straightforward question. Okay. Now the main question comes, that identify the NO stretching frequency of nitrobenzene in its IR spectra, which is shown below. Okay. So here nitrobenzene like this. This is one resonating structure. Another resonating structure will be H4 equivalent. Now the question is, identify the NO stretching frequency of nitrobenzene in its IR spectra shown below. Okay. So here from the IS spectra given, a lot of spectral informations are given corresponding to double bond or NO or CN bond, anything. This is given here. From there, you just need to find out for NO what is there given. So I have told you that for NO symmetric stretching and asymmetric stretching, these two things are possible. Okay, that I have told you. And also told you that nearly 13,000 centimeter inverse, there is some band corresponds to CH stretching and some band correspond to asymmetric stretching that we will found nearly 15,000 centimeter inverse. Okay. So you see here one band is there, it is almost 13,000 something, and one band is there which is almost 15,000 something. Okay. So these two bands are generally present due to the NO. Okay. Due to presence of NO, symmetric and asymmetric stretching, these two bands are generally coming. Now, which one will be the symmetric one? The symmetric one will be this one, right? We'll have less energy symmetric, and this one will have asymmetric. And since you are not asked to find any other, I mean, in the groups in this spectrum, so you don't need to do that. You just need to find out the NO stretching and NO symmetric and NO asymmetric stretching. So this is the answer, that they are symmetric and asymmetric stretching of NO. Okay. Now, cyanobenzene is given. So you need to assign all the prominence bands in the IS spectrum of benzonitrile shown below. Okay. Suppose you are given such kind of questions. So you need to find out that which kind of bands are you expected to see in from the structure of the molecule, and then you match that where it should come. Okay. So since cyanobenzene is given, you see which functional groups could be present here, and you see which functional groups could be coming, and you just identify that, match with the IS spectra, you will get the results. So in case of cyanobenzene, what kinds of groups you expect in the IS spectra? What kinds of groups? What kinds of group do you expect? Functional group I am talking about. Yes.
Amines.
Hmm?
Amines.
Amine. Okay, first of all, there is no amine. This is cyano group. Okay. This is not amine. This is cyano group. Yes.
2250 centimeter inverse.
First tell me how what groups will you need. Then we will match.
We have the nitrile function.
Nitrile. Okay.
Then CHF aromatic.
CH aromatic.
C double bond C aromatic.
C double bond C aromatic.
Monosubstitution aromatic.
Monosubstitute aromatic. Then which bond?
Come again?
Which bond? Monosubstitute aromatic means you need to find some bond, right? All are bonds.
Yeah. That means we have 5 CH bond which is left out in the aromatic region.
These hydrogens?
Yes. Since
So
they have them,
aromatic.
that means one of the hydrogen is missing out. That will be called as a monosubstitution conformation in the structure.
Yes, but CS, yes, you have told the CH aromatic already.
Yeah.
Anybody else? Anything else? I think all are done. CN, CA, CC, right?
We have CN also is there. C single bond N.
C triple bond N.
Triple bond N, yes.
Triple bond N is the nitrile group, right?
Okay.
So where you expect the CN, where you expect the CH, and where you expect C double bond C?
The one which you already made a bracket is for the C double bond C aromatic.
Yes.
1600 to 1400.
Yes. Why there are too
And
many
it-
bands?
is the
Try it. You
due
will
to the
get.
delocalization of pi electrons?
Yes. Why? Why?
We have vibration bands starting from 1400 to 1600.
Because now I am asking that why so many bands are there? We have only one kind of C double bond C, right? So that means
But,
different kinds
but
of
the
bonds
pi electrons are not stable to pi. These all been delocalized.
because of
Delocalization of pi electron in the aromatic ring system, and also due to the
cyanide group. This will take the
cyanide.
electron density. Okay.
Mm.
So C double bond C will have a number of values, 14,000 to 16,000, and also you see here there is no aromatic carbonyl, so you don't need to worry about that one. So it is completely C double bond C. Now, where
I'm not
you
clear.
Mhm.
You are saying that because of the cyanide group only, you have so many bands coming from 1400 to 1600.
Yes,
And
because
suppose if it is
cyanide group,
if it is only aromatic ring of benzene, will you get peaks here like that?
no,
We'll have only one peak.
only one thing. So cyanide group is attached here. So this double bond, this will have we actually have different strength. Okay. So we will
Okay.
see that also the C double bond C will have in this region. Okay.
Oh,
Okay. And benzene case, I guess benzene case, one more thing you can see, if there is some symmetric or asymmetric stretching of the C double bond C, then you can expect something. Okay. Yeah. Now, C triple bond N, in this case, C triple bond N, where it should come?
little more higher frequency because of triple bond force constant.
It generally comes in this region. Okay. 24 to 1000 almost. 3 or 23,000 or whatever it is. Okay. This centimeter inverse, this region is actually assigned to Cn. And this region is actually 16,000 to 14,000 centimeter inverse. Now one thing is missing, which is CH aromatic, where it should come.
Around 3100 centimeter inverse.
Exactly. Yeah, exactly. Yeah, this is. So this is nothing but this is Cn. This is CH. Since it is sp2 carbon, sp2ch. Okay. So all the things I have written here, that sharp peak at 2015, 2250 centimeter inverse, this corresponds to Cn. Sharp peak at this corresponds to aromatic CC bond stretching. 700 and 780 centimeter inverse, this corresponds to out of plane bending. This coming, this 700, this one and this one, this is coming due to out of plane bending vibration. Okay. Of CCH bond. You don't need to assign all that because generally in many cases you don't need to this assign this fingerprint region. Okay. Main functional group generally comes in this region, and also you see this 13,000 3060 centimeter inverse corresponds to aromatic CH. What I have told you here. Okay. So you have assigned all the compound groups that is present in the cyanobenzene. Okay. Now,
Sir,
yeah.
in previous molecule we have three types of CH bond, no sir?
3 types of
CH bond.
which case
Previous
here.
due to no, not this CN molecule.
CN, yes.
Here we have three types of CH bonds, no sir, around. Due to
CH,
CN position, there will be three types, no sir, protein.
this one, na?
Ortho,
Ortho meta beta, right?
uh,
So this is ortho
yes,
hydrogen.
yes sir.
Okay. So that doesn't differ much. Okay. See this single substitution. So
It
this
won't,
CH actually does not differ much. If you have another substitution, then that will differ much.
okay. Then, okay, okay, sir.
Now you need to find out this compound.
Sir, I have a doubt.
Mhm.
Why there are two peaks for C double bond C stretching?
Okay, since this region, this is not two peaks, this is also included. Okay, I have written here 1580 peak. This peak is also there. This region. Okay, you just have your C double bond C. You need to see that in this region, if there is some peaks are there or not. Okay, so
Okay, sir.
sometimes different interactions may give to different number of peaks. Just you need to see that in this region, whatever you are want to find, that if there is any C double bond C peak, if there is not. Okay.
Okay, sir. Okay.
Okay. Now here what is the name of this compound? This is N-methyl N-methyl aniline, right? So I need to confirm from this IR spectra that whatever structure they have predicted is correct or not. So what are the functional groups you find here? What kinds of functional group?
Sino.
Cyano. Cyano? Very cyano. NH could be possible. Okay. In this sp3 carbon CH, they generally come in this region. Okay. So I'm not interested in now in this region. This is called fingerprint region. I'm not interested in that. I'm interested in NH. One thing is aromatic carbon double bond carbon. Okay. What is it possible? Aromatic CH, right? Double bond C and H. This is aromatic CH. And one is sp3 carbon CH, which is this one. Mhm. So you need to find out in which region they are expected to found, and you see if there is any peak in this region or not. So first coming to NH1, where do you expect NH to found?
Around 1600.
It is beyond 3000,
Yes.
where we have somewhere around 3000 to 3500. We
Mhm.
have a single peak that is clearly indicating second Raman, where it is primary Raman will get two peaks.
Someone's mic is also open. Please mute it. Yeah. Yeah. What you were saying? Hello?
Yeah, it's the single medium peak which is coming beyond 3000 indication of NH stretching of second
One?
Raman. And the higher frequency. Yeah,
This
that's
is,
one.
yeah,
That is the one.
that is NH.
Yes,
Exactly. And how from here you know that it is primary, secondary, tertiary?
definitely.
Yes, because only one peak is there. If it will
Yeah,
be
yes,
primary, then it will be two peaks. So since
yes.
you are seeing only one peak, this is NH. Okay. Anything else? C double one C? This region. The same thing, right? 16,000, 14,000, this region, right? I told then the last question. Okay. Double bond CH mean these hydrogens. Two types of CH is here. One is double bond carbon hydrogen and it is single carbon hydrogen. Which one will be there?
Below 3000 is saturated, above 3000 is sp2 of
Yes.
Region
aromatic.
of
That
3000.
is this region, right? Right? This region, right?
Below 3000 is CH saturated.
Below 3000,
Yeah, that is for CH3.
CH saturated means this CH3, right?
Yeah, and above 3000 is aromatic.
Correct. Exactly. So I have told in the initial stage that for this CH, I not right, P3 carbon CH. So I have told you that if there is a double bonded carbon and hydrogen is attached, I have also solved a question that will have higher frequency, and you are seeing it here that the higher one will be due to sp2 kind of CH. Okay, and here sp3 kind of CH will be this one. Okay, so this is the answer, that you have need a sharp peak at 13.3450 centimeter inverse due to NH, 16,000 and 14,090 due to aromatic CC, 3000 to 3100 centimeter inverse corresponds to aromatic CCH stretching vibration, and also the peak at 28,000 to 3000 centimeter inverse corresponds to sp3 carbon hydrogen. Okay, so up to any question up to now?
Sir, I have a doubt.
Sure.
I have somewhere written in my notebook that NS bending NS bending we find at 1620 centimeter
Yes,
inverse.
yes,
What is
yes.
this?
We are interested in NH stretching. Bending
Sir,
is
is this
done by
amine?
the. Mhm.
Is this amine?
This is secondary. I mean,
Secondary amine.
what is this
And
one?
first, I have doubts, sir. I can't understand this.
Acha, okay.
This is primary amine.
This is primary amine.
Secondary amine. Secondary amine. Sorry, sir.
Okay,
Secondary
first
amine.
confirm. What is this?
This is secondary amine.
Okay. Now, I have two R's. This is secondary amine. I'm still now in secondary amine.
Yes, sir.
Okay. Suppose I replace this R with methyl. Okay. And in this R position, I am writing phenyl. So what we will see? So phenyl, I am written one bond will be there. N, one hydrogen will be there. Another will be methyl. So this is the structure. Now you understand why this is secondary amine.
Yes, this is secondary amine.
Yes. So if secondary amine is there, you will see only one band. In stretching,
At what,
in
sir?
stretching.
What is the frequency?
This is 3450 centimeter inverse. Almost that range. You see, find in that range is the 3300 to 3500 in that range, I guess. That range you will find NH. To find in this region, if there is any peak, you can then assign it. Okay.
Okay, sir. That means secondary amine we will find a peak around
In primary amine,
3400.
primary amine, if you primary amine will be there, you will find it again there, but there will be two peaks that I have just talked about. In secondary amine, there will be one peak only. Okay.
Okay, sir. Thank you, sir.
Anybody else?
I have three clarifications.
Three clarifications. Okay.
Yes. This is regarding to the introductory part of a lecture where you mentioned about two types of instruments starting as dispersive and FTIR. I was not clear with the instrumentation part. If you take any spectroscopy, particularly with UV spectroscopy, we have this sequence of arrangement of instruments like your light source, monochromator, sample holder, detector, recorder.
Right.
But in dispersive IR, we keep in a slight change in the order, saying that after the light source, we keep your sample holder, then we place your monochromator. I just want to know the reason, sir.
You have read fluorescence? Have you read fluorescence?
Yeah.
Fluorescence where monochromator is there?
We have two monochromators we use. One is primary, the other one is secondary. If it is a filter instrument, it is a filter, and if it is spectro, it will be monochromators.
Yes. So fast monochromator is actually used to choose any one of the wavelength, right?
That is for excitation and emission. But my question is here in IR.
Okay. I'm coming to a question. I'm coming to a question. So you would just choose only one excitation. Multiple lines are coming. You just need to choose that which you want to get all the wavelengths singly. That's why you use monochromator. Otherwise, all the lights will come at a time. Okay, that's why you use monochromator in the emission. Second
Yeah,
monochromator, correct? Now in IR, whatever you do, you will first give all the light to your sample. Now sample absorb. Now it will, some group will absorb 17,000 light, some will absorb 18,000 light, some will absorb 19,000 light. Okay. So whenever you are recording your spectrum, if you don't use any monochromator, what will happen? All will come again. There will be a mess up. You just need to see that this light I have passed. Now I need to see that if this light is absorbed or not. I need to meter that I want this wave number of light, and now I want to see if this is absorbed or not. This is the thing that you need a monochromator after the sample is absorbing the light. You have got the point?
I'm not clear, sir.
Okay. Okay.
No,
You have,
I just explained my understanding. When you use any light source, we may not get exactly the light what we wanted to have the measurement of a sample. For example, in case of UV, if I wanted to have a measurement 254, I have to select that only 254 to pass on through a monochromator, and that should be interacted with the sample. Correct? That is the purpose of using either a filter or a monochromator. But on the other hand, if you go with IR, we pass all the light together from the light source directly into the sample holder. And then later on, we are allowing the light to pass on to our monochromations.
yes. The opposite
So,
thing is happening. That you are
yeah.
telling, right? So in UV, what level do you probe? Electronic
Okay.
level.
Yeah.
But here what do you probe? Is vibrational level,
Vibration.
right?
Yeah.
So whenever you are using any any IR light, it is actually giving all the lights at the same time. Okay, in case of UV, you have used one light, you see if it is absorbed or not. Okay, then it will come. Now it's your choice. Okay, just like in fluorescence, that was I was talking about. Fluorescence is giving all the lights. Somewhat basic, somewhat intense, more intense, somewhat less intense. You need to collect one by one, right?
Yeah.
The same thing IR is using. It is taking all the lights that matter. Some group absorb. Now this light, they are monitoring that. Okay, this 17,000 is absorbed by how much? Okay, then pass this, then pass 18,000. This is absorbed by how much? Okay, this is a technique. The same technique is used in fluorescence spectroscopy also. Okay.
But in fluorescence, we are using again the
You are
components
using a single
before the sample holders.
Before the sample holder, and again you are using when sample is passed, the light is passed through the sample and it is emitting, then you also use a monochromator, right?
No, my understanding with the spectroscope is monochromators are used only for selecting a suitable wavelength to interact with the sample.
Exactly. No. Monochromators, yes, whatever you are saying, but not to interact with the sample. If
allowing the specific wavelength of light to
whatever
interact
you
with
need, you just use a monochromator. That I need this light, I use some monochromator, right? So one by one, if I want to see that which one is changing or which one is not changing, that's why monochromator is used. That it passes not all the lights at the same time, but it is passing light one by one. The other thing happened with UV, that they passes one by one light and they monitor it, right?
Okay, sir.
Okay. Anything in another two?
Sir, what is S character and P character?
Sorry.
Sir, what is S character and P character? In the previous slide we discussed.
Okay, I'm coming to these two questions. Yeah.
Let me complete the other two, sir. Then you can take this.
Yes,
I told three questions.
Yeah.
Question number 2, we have mentioned about polystyrene, which is going to be used as a calibration.
Yes.
But can we use this one for both the FTIR instrument as well as for the dispersive instrument?
If peak positions are same, that is reported. Okay, I actually don't. People nowadays don't use this dispersive IR. Okay, nowadays people generally use FTIR.
Okay.
So if any polystyrene gives you the same peak, I think they should give the same peak positions. If the same peak position, you can use for both of them.
Okay. Okay. And that higher frequency value of around 3000 plus is coming due to what, sir?
Which one? In which case?
You mean polystyrene? You mentioned there are two peaks which is appearing. One at around 1600. The other one at 3062. The 3062 is due to the aromatic carbon hydrogen, sir.
Right.
Okay. And still the last one, I'm not still clear with that variable multiple stretching bands for the carbon-carbon double bond of aromatic system. What is the reason, sir?
Okay. First of the thing that I have told, the same thing. Okay, this case it could be the reason that this group is rotating, and so these hydrogens will feel different electron density, and they will give different kind of this vibration. But actually, this splitting pattern here is that much not important. You need to find that in this region where you suspect that your CH could come, whether there is a peak or not. Okay. So if first of all you see if anyone is doing any kind of spectroscopy to identify a molecule, they first don't do IR. Okay, because IR cannot tell you that yes, this is the molecule. If you have some molecule which you have confirmed from mass or NMR, and if you want to confirm using this IR, then you will do it. Okay.
Okay, sir.
Okay. Now one thing what one is asking is character.
And P characters.
Is and P character. You know hybridization?
Yes, sir.
What kind of hybridization are possible?
1s2, 2s2, 2p2, 2p, and
No. I am asking about hybridization. You are telling me this electronic configuration.
electronic configuration.
Okay. Do you know this kind of three types of hybridization?
Yes, sir. So, triple bond, single bond sp3 hybridization.
Generally, single double bond has hybridization, right?
Sir, yes, sir.
Triple bond has sp hybridization, and single bond generally have sp3 hybridization. Okay.
Yes, sir.
Now, suppose if 100% is your orbital character and sp3 is contributing, you will see 25% character will come from s. 3 p are since involved, so 75% character will be of p. Okay, so to make this orbital, how much s is involved? 1s. How much p is involved? 3p. So 25% will be contributed by s. 75% will be contributed by p. 25% by each p orbitals. Right?
Okay, sir.
Similarly, now I am going to sp. What will be the ratio? If 100 among 100%? 1s and 2p. So
2p.
33% will be s character and everything. And 66% will be p character. And since 2p are involved, so 33 for each. Right?
Yes,
now
sir.
I am going to sp.
Okay, sir.
SP
50,
will
50.
have 50-50. So which one will have higher s character?
SP, SP3, sir.
How? SP here is 50%, here is s character 33%, and here is s character 25%.
SP, sir. SP.
Now we
Yes,
understand which one is s character, which one is p character.
Yes, sir. Yes, sir. Thank you, sir.
Okay.
Hello, sir.
Yeah.
Sir, yeah, I have a doubt regarding the 10th question. Means actually, in 9th question we have means also considered a prominent peak at 700 and 780.
Yeah.
Or-
Here you can also consider. Okay. I'm
Okay,
actually
yeah.
what I'm saying that this is called fingerprint region. Okay. So since here all the peaks you will see CN, CO, all the single peaks, they will generally come here. Okay, and their bending modes all will come here. So there people generally don't consider generally after 14,000, about after 1,000 centimeter, people are generally considered. So I am mainly interested in this. I have to confirm that what structure I have predicted is correct or wrong. So I have taken only this region. Okay. If you want to see bending, you can see there.
Okay, yes.
Okay. So I don't think anybody have more questions. If you have, you can ask.
Sir, as we explained, for any spectroscopic transition moment integral should be non-zero.
Exactly.
That is, dipole moment should be non-zero. Sir,
Yes.
NMR is also a spectroscopic technique, and in that case, we can't. Sorry, we do not talk about dipole moment.
Dipole moment, because the expression of this transition moment integral. Okay. So I have told you about transition moment integral. That is not a dipole moment. In this case, this is dipole moment. So if you see direct the quantum mechanical calculation, you will see here only dipole moment vector will come. Okay. But for NMR, dipole moment vector will not come. Okay.
There will be another factor which should be non-zero.
Exactly. Any spectroscopic transition, you will see there will be some factor that will be non-zero, which will make this transition moment integral to be non-zero.
Okay,
Okay.
sir. Okay, sir. Got it, sir. Thank you.
Sir, what is the non-zero factor in UV, sir?
What is the?
No, you said any spectroscopy there will be some moment will be non-zero. In UV, what would be the factor which is giving non-zero, sir?
If you see this, okay, Frank-Condon transition, you know, Frank-Condon principle.
Is it something like a Jablonski diagram?
Yes, from Jablonski, Frank-Condon transition actually tells that electronic transition should be vertical. Okay. Okay, electronic transition should be vertical. So in electronic spectroscopy, if you just going to write this transition moment integral, okay, so you will see if this term will also not come. If this is not coming, your this transition will be non-zero. Okay, the states will be like that. That will be non-zero. Okay.
Okay. Okay.
Okay. So I am stopping the recording.